Lewis structures. That's what we're going to be covering in this very first lesson in the very first chapter of my new organic chemistry playlist. Now, in this first chapter, it's pretty much going to be a review of general chemistry. We'll start off with Lewis structures, move on to formal charges, hybridization and valence bond theory, molecular orbital theory, which I call it again a review from Gen Chem, but that's often a place where we skimp a little bit in Gen Chem, so might be a little less review in that particular section. And then we'll finish this chapter off with a discussion of polarity and intermolecular forces. Now, because this is the first lesson in the entire playlist, let me give you just a little bit of an introduction to the organic chemistry playlist here. So this is going to be very similar to my old playlist, but I'm going to be using a whiteboard instead of PowerPoint and a green screen. So a lot of you have said you much prefer the whiteboard instructions, so ask and ye shall receive. So I'm going to be releasing these weekly throughout the 2020-2021 school year. So if you don't want to miss one of these, subscribe to the channel and click the bell notifications, and you'll be notified every time I put one of these up. Now, because this is the first lesson in the first chapter of the entire course, I do want to give you just a little bit of an introduction to organic chemistry. So organic chemistry, as contrasted to inorganic chemistry. So we look at organic chemistry as just the study of molecules you find in living systems. Now, they used to think that there was something special called the vital force and things of the sort. I don't really care about that. But the big thing you need to know is that this is going to be the study of carbon-containing compounds. That's the way we're going to look at organic chemistry. We're not going to talk about, like, it's the study of growing things without pesticides and natural growing, whatever. It's all about carbon. So whereas inorganic chemistry is going to deal with all the rest of the elements, here we're going to deal with primarily things involving carbon. So, and this is going to be a beautiful thing because we're pretty much not going to talk much about transition metals, and this is going to actually simplify and focus on what we really need to study in some of this review of Gen Chem here. Now, one other quick note about organic chemistry. So it is not taught exactly the same from textbook to textbook, professor to professor, university to university. So I'm going to be shooting for kind of middle of the road organic chemistry course. And where I know there's some variability in what's presented, I'm going to let you guys know. And I'm like, hey, some of you guys might see this way, and some of you might see it this way. So, and things of a sort. And it's not that one's right and one's wrong. So, but it turns out that organic chemistry and life in general, reality, is very complex. And so sometimes instead of giving you the exact level of detail that we know and understand about organic chemistry, we often just give you some trends and then kind of try to make some absolute rules out of them and then don't tell you that that's what we're doing. So when I know that something's often commonly presented in more than one way, I will make particularly note of that and I'll let you know. And I'll say, hey, by the way, pay particular attention to how your professor presents this topic. So, and this is not going to happen super often, but it will happen in a few key places throughout the course. All right, so let's talk about Lewis structures. Now, in a Lewis structure, we put valence electrons on there. So you got to know how to remember, how you identify how many valence electrons an element has based on where it is on the periodic table. So in the group 1 elements, hydrogen on down, they've got 1 valence electron. Group 2 elements, beryllium on down, have 2 valence electrons. Boron's column 3 valence electrons, carbon of particular note, 4 valence electrons, nitrogen 5 valence electron, oxygen 6 valence electrons. The halogen 7 valence electrons, and then the noble gases 8 valence electrons, which we really don't care about them. They're not going to be involved in any bonding that we'll see in this chapter. But that's kind of how you identify that. And also of note is you can usually figure out based on that how many bonds an atom is typically going to make. Now, it's not absolute. Sometimes you'll see carbon with a different number of bonds than its normal number of 4. So, but we can predict that carbon can make 4 bonds, for example, from this info. So the way this works is you look at how many electrons is an atom short from getting a filled octet. That's usually its typical number of bonds. So like the halogens here, they have 7 valence electrons. Well, that's 1 short of a filled octet, and that's why you typically see them making just 1 bond. So oxygen's column on the other hand, so they've got 6 valence electrons, and 6 is 2 short of a filled octet, so they're typically going to be involved in making 2 bonds. So nitrogen's column typically going to make 3 bonds. Carbon's column typically 4 bonds. And then we'll go back to boron here, and you would say 5 bonds, except that would be a violation of the octet rule, and you find out it drops back down to 3 bonds. So, but let's talk about that octet rule. So the octet rule talks about, most atoms are going, struggling in their existence to have 8 valence electrons. And we should talk about where that comes from first. And so in any typical subshell, or I should really say shell, there's going to be an S subshell and a P subshell. for where electrons can live. In the s subshell, there's just one orbital, and so you can only put 2 electrons there. So, but in the p subshell, there's 3 orbitals, and so you can fit a grand total of 6 electrons there. So 2 per any orbital in the universe here. So we'll put 1, 2 there, and then 1, 2, 3, 4, 5, 6 for a grand total of 8. So this is where the octet rule comes from. It's just how many electrons can you fit in a typical shell is the way this works. So for like carbon, he's shooting for 8, things of this sort. Now, boron here we'll find out is an exception. So he goes under the octet rule, and then we'll find out that some of these bigger guys can go over the octet rule. And so you really need to understand these exceptions as well. So first we'll start with what's called an expanded octet. Now the truth is this is not the most important one for organic chemistry, because for organic chemistry, we're really going to be focusing on these guys. And it turns out they're not allowed to go over the octet rule. So what is special about, say, sulfur that lets him go over the octet rule? Well, first off, it's not just sulfur. It's anybody in this third period of the periodic table and lower. And what's special about that is starting in the third shell, in addition to the S and P subshells, you're also going to have a D subshell. So, and the D subshell lets you put more electrons in there, up to 10 more if you want to. So here's the deal though. So you only start having a D subshell in the third shell or above. So a third shell and above corresponds to the elements in the third period and below on the periodic table. And that's why they're allowed to go over the octet rule. Now they don't have to, they're just allowed to. Cool, but we're not going to be dealing a lot with these because most of the chemistry we're going to study is going to involve like carbon, nitrogen, oxygen, and then hydrogen quite a bit. So now you might see this in an inorganic reagent like sulfuric acid. We might see it in him. In fact, we'll stick him up on the board real quick. Sulfuric acid. So I won't draw in all the lone pairs and everything, but you can see sulfur ends up with 2, 4, 6, 8, 10, 12 electrons around him way over the octet rule. And now again, sulfur is not always going to violate the octet rule. He doesn't have to violate the octet rule, but he does have the option of going over the octet. And again, we call that an expanded octet. Now your second example, and this one will come across a little more frequently, is going under the octet rule. So, and hydrogen definitely goes under the octet rule. So oftentimes we say that when an atom satisfies its octet, it looks, at least from its electron configuration standpoint, like a noble gas. Well, hydrogen is just trying to look like helium. And in the first shell, there's no P or D, there's just the S. And so if you're in the first shell like hydrogen, you only want 2 electrons, not 8. And so oftentimes, we'll see hydrogen always actually going under the octet rule. So, but turns out beryllium also, now beryllium's more of a metal than a non-metal, so you're not going to see it making covalent bonds too often, but maybe you'll come across this in this first chapter. But beryllium only has 2 valence electrons, and he's like, I'll share one with you, and I'll share one with you. And so with beryllium, we often see beryllium only making 2 bonds like we do here in BeH2. And as a result, he only ends up with 4 electrons around him total. So it goes under the octet rule, and that's pretty typical for beryllium. So we'll see the same thing actually with boron and aluminum. So if we look at boron here, in BH3, at least in this particular version of drawing the Lewis structure for BH3, we see that boron with 3 valence electrons can only share with 3 different atoms to make 3 bonds, and ends up with only 6. Now, there are cases where boron will end up with 4 bonds and end up with a filled octet, but what I'm saying is that it's normal, it's typical for him to only end up with 6, not 8, and therefore he goes under the octet rule. And again, both boron and aluminum often only get 6 and go under the octet rule. Cool. So third row and lower can go over, but we see in hydrogen, beryllium, boron, aluminum, they all have an option of going under, and it's pretty typical for them. Now, the last exception to the octet rule is pretty much not going to be relevant to organic chemistry. And if you've got a species like NO, which overall has an odd number of valence electrons, then somebody's going to have an odd number, which is not 8 as a result. But we're really just not going to encounter this in organic chemistry, so I put it on your handout there, and I put it on the list, and I'll put it up on the screen here. But the truth is, you're probably got about a 0.001% chance of ever encountering it in organic chemistry. All right, so there's our exceptions to the octet rule. So now we need to work on, how do we accomplish getting a filled octet? Well, there's one of a couple different ways. And so one of them involves having a metal and a non-metal. And the way we draw Lewis structures for elements is you just look at how many valence they've got, and sodium's got 1. And so we'll put 1 electron here for sodium. And then for chlorine, we've got 7. And so you put them on the 4 sides, you might recall. So 1, 2, 3, 4, and then start pairing them up. And so there's our 7. And in this case, when you have a metal and a non-metal, well, it turns out non-metals love to gain electrons. And metals, I won't say they love to lose electrons, But if somebody's got to lose an electron, the metals have rather low ionization energies, and they're the easiest ones to remove one from. So here chlorine says, hey, sodium, give me your electron. And sodium says, okay. And that electron's going to get transferred over. And as a result, we're going to end up with a sodium no longer having that valence electron, and a chlorine now having 8 valence electrons. And it turns out with chlorine now having 8, he's got what's called a negative formal charge, and we'll deal with that a little more specifically of how you'd calculate that here later. And sodium's going to have a positive charge, and they now would potentially be ionically bonded together. Now, we're not going to deal with ionic bonds very often in this course. They will come up on time and again, but most of the time we'll be dealing with covalent bonds. So with an ionic bond here, we get the complete transfer of electrons, and the result is that now chlorine's got a filled octet. And you might be like, well, sodium's got nothing. Well, sort of, but sodium actually still has a complete second shell that's full. And in that sense, he's still got a filled octet as well. And so now by a transfer of electrons, when you have a metal and a nonmetal, that's how you achieve your filled octet. Now, what if you've got 2 nonmetals? So say I've got 2 chlorine atoms. So 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. Cool, and this chlorine says, hey, chlorine, give me your electron. And this chlorine says, no, give me your electron. And the problem is now we only have 2 elements that both want to gain electrons, but neither one is going to lose one very easily. They have rather high ionization energies. So in this case, there's no transfer of electrons. It's not possible. So we have nobody who's willing to lose one, but they can share. And so they're going to put their electrons together and share them. And the result's going to look like so. Cool, and there's our 2 shared electrons, and much more commonly, you might recall that we represent those shared electrons as a line to represent that covalent bond. And so those 2 shared electrons are a covalent bond. And now the chlorine on the left gets to say, hey, I've got 2, 4, 6, 8 around me, and the chlorine on the right says, I've got 2, 4, 6, 8 around me. They both get to count those shared electrons as part of their octet. And so sharing now accomplishes getting a filled octet in this case. So if you've got 2 nonmetals, and for organic chemistry, we're going to almost exclusively be dealing with nonmetals most of the time. That's why we're going to be dealing much more commonly with sharing electrons rather than a transfer of electrons like we saw in the first example. So let's draw some Lewis structures. So we're going to draw 5 Lewis structures here, the ones we got outlined here. In this case, we're going to start easy, and then we're going to work our way to make it a little harder. And then we're going to finish this off with a couple examples of very common organic molecules you might encounter, both in this chapter as well as later on in this course. Now, we'll start with CH4, and we're going to start off easy here. And first thing you want to do is just figure out how many valence electrons you got to work with. And so, again, carbon's got 4, and each of the hydrogens got 1 each for 4 more, for a grand total of 8 valence electrons. Second thing you want to do is figure out who's your central atom. In some cases, you might have more than one. But who's your central atom, and then set up a skeleton for your molecule with connecting all the atoms by single bonds. And so in this case, your central atom is typically the one that can make the most bonds. And you might recall that the halogens, being 1 short of a filled octet, typically make 1 bond. Oxygen columns, 2 bonds. Nitrogen's column, 3 bonds. Carbon's column, 4 bonds. Boron's column back to 3 bonds, and then hydrogen just a single bond. And so in this case, the way that usually works then is usually you can make more bonds as you move this way up to a point. And so usually we like to say that there's a pattern where typically the least electronegative atom becomes the central atom, except just not hydrogen, because hydrogen actually is less electronegative than carbon, but carbon makes way more bonds. So if kind of a general rule, it actually works most of the time. So the least electronegative atom will be the central atom, just not hydrogen. All right, so in this case, we'll put carbon in the center, and we'll set up that skeleton. So we'll connect carbon to all of the hydrogens with single bonds. Cool, and next thing you'll do is you'll fill up the outside atoms. Well, in this case, the hydrogens don't want a filled octet. They just want 2 in order to look like helium. And so in this case, they've all got 2 around them, and they're full. And so at that point, you'll always have enough electrons to fill up the outside atoms. So then you move to the central atom, and any electrons left over at this point go on that central atom. And sometimes you'll have some left over, and sometimes you won't. So this is your first point where you got to take an accounting. And in this case, we had 8 electrons to work with, and we've used all 2, 4, 6, 8. So there's none left to give the central atom. And once you're out of electrons, then you ask, is the central atom satisfied? And usually that means, does the central atom have a filled octet for those that are following the octet rule? And in this case, carbon's following the octet rule. And he's got 2, 4, 6, 8, and he's got that filled octet, and so I like to think he's happy, and that makes this your structure for CH4. But this is kind of the general pattern we start off with, you know. So figure out your valence electrons, figure out who goes in the middle, and set up your skeleton. So fill up the outside atoms first, any additional go in the inside atom, and then we'll see if we need to take it further. We didn't in this example. We'll see what to do in the next couple. So the next one here is ammonia. So nitrogen's got 5 valence electrons. And again, each of the hydrogens got 1 each, so for another 3. And once again, we've got 8 electrons. Now, nitrogen being the least electronegative, besides hydrogen, goes in the middle because it can make the most bonds. And so we'll set up our skeleton here. And at this point, we'll then fill up the outside atoms, but these are hydrogens and they're already full. And so then we got to do our accounting again. This is the one point where you got to do an accounting and figure out, are there any electrons left to give the central atom? Well, in this case, we've used 2, 4, 6. We've got 8. Yeah, we've got electrons left over. And when you've got electrons left over after filling up the outside atoms, you always put them on in pairs on that central atom. Well, we've only got a pair, so we're going to have to just put 1 pair on that central atom. And now that we've used all 8 electrons, we're out of electrons. You ask, is the central atom happy, or is the central atom satisfied? Does he have a filled octet? In this case, 2, 4, 6, 8, he's got a filled octet, and he is indeed happy. And that's your structure for NH3. So let's see another example here. So H2CO, each of the hydrogens got 1 valence electron each, carbon's got 4, and oxygen's got 6, for a grand total of 12 valence electrons. Now in this case, carbon is the least electronegative besides hydrogen, and so carbon, being able to make the most bonds, goes in the center. So we'll put carbon in the center, surrounded by the others. And in this case, we say, okay, fill up the outside atoms first. Well, again, the hydrogens are full, but oxygen wants a filled octet, and he could definitely use some more electrons. And then you say, are there any electrons left for that central atom? Well, in this case, we've used 2, 4, 6, 8, 10, 12, and there are none left to give carbon. And now that we're out of electrons, we say, is carbon happy, or is carbon satisfied, or does carbon have a filled octet? And in this case, he doesn't. He's only got 6 around him. But we can't put another lone pair there because we don't have another pair of electrons to give. And when you get to this point, when you've run out of electrons, your central atom is not happy, somebody next to him needs to share. And in this case, the only atom that's got any electrons to share, lone pairs, is the oxygen. And so the oxygen is going to share a pair. We'll erase one of these lone pairs of electrons, non-bonding electrons, and make them bonding electrons to carbon instead, in this case a pi bond. And so now we've got a double bond, and now carbon's like, oh great, I feel good now. I've got 2, 4, 6, 8 electrons around me. Now everybody's got a filled octet, and this is your Lewis structure for H2CO. So these last two are a little more complicated. And these are typical organic molecules, and these are what we call condensed formulas. So we'll talk about these in chapter 2 in a little more detail, but for now you should realize that they give you a nice way of representing a little more complicated molecules. And one thing you should know at this point, when we put a carbon followed by hydrogens, those hydrogens are going to be bonded to that carbon. So in this case, when I see CH3, I know that these 3 H's are bonded to that carbon. And suffice to say, that's going to help you set up your skeleton. But in this case, we've got 2 carbons, 4 valence electrons each, that's 8. An oxygen, that's another 6 for 14, plus 4 hydrogens, another 4 total, for a grand total of 18 valence electrons. Now, with more complicated molecules here, we're going to find out that you don't necessarily just have one central atom. But kind of again, use that condensed formula to kind of piece together what this looks like. So we've got this first carbon that's bonded to all 3 of those hydrogens. And then he's also bonded to the next carbon in the chain. And then he's bonded to that hydrogen. And then he's bonded to that oxygen as well. So really, both of these could be viewed as being central atoms in this case. Now, we're going to fill up the outside atoms next, and we've used 2, 4, 6, 8, 10, 12 electrons. We've still got 6 left, but you're always going to have enough to do those outside atoms. Well, the only outside atom that's not full is oxygen, because the hydrogens are all good. But that oxygen will give him 3 lone pairs. And now we've used all 18 electrons, and we have to ask, are all the central atoms happy? Well, this one on the left, he's good. 2, 4, 6, 8, he's got a filled octet. But this one on the right is not. He's only got 2, 4, 6. So in this case, how do you give him that filled octet? Well, again, once you round electrons, if any central atoms are not happy, somebody next to them needs to share. Well, the only atom that's got lone pairs to share next to this carbon is the oxygen. And so just like on the last example, we'll erase one of these lone pairs and make another bond. And now this carbon's got a filled octet, 2, 4, 6, 8. And this is the proper Lewis structure for CH3CHO, and we call this an aldehyde, so which we'll get to also in chapter 2. Not important for now though, but a very common type of organic molecule, and you'll want to get to the point of recognizing what this kind of structure is going to look like, especially the end of this, based on seeing this kind of condensed formula. So cool, we just kind of derived what this Lewis structure looks like, but by the end of chapter 2, you're going to want to memorize what that Lewis structure looks like. All right, so this guy right here is acetic acid. It's the main non-water component in vinegar. So, and it's what we call a carboxylic acid. So in this case, if we're going to set up our Lewis structure, first thing we're going to do is count our valence electrons. We got 2 carbons, that's 8, 4 hydrogens for another 4 more, and that's 12, and then 2 oxygens, 6 each for another 12 to get us to 24. Now we'll start with that first carbon and set up our skeleton. He's bonded to those 3 hydrogens next to him. And then he's bonded to the next carbon in the chain. And here's where things are not going to be so clear cut. So here you might be like, it's COOH. Well, one, we know this carbon is not bonded to the hydrogen, or else it would have been written right next to that. Okay. But we might be tempted to try and do this. So, and it turns out there's not a great way to make this work. But there's no way for you to know that up front, but we'll work it out and then figure out why it doesn't work, and then we'll start again. So in this case, we got a lot of central atoms here and stuff like that, and we'll fill up what are the outside atoms, which is a little bit nebulous, but in this case, I'm just going to fill up the more electronegative atoms first, but we've used 2, 4, 6, 8, 10, 12, 14. We got 10 electrons left, so we've got plenty of electrons. I'll give them to the more electronegative oxygens first, and that leaves me to give 1 pair to the carbon, and then we say, are all the central atoms happy? Well, no, this is the only one that's currently not happy, no filled octet, only 2, 4, 6, and so we might say, well, why doesn't one of the atoms next to him share? Well, we can do that, and we come up with a problem. And we'll find out that this really comes down to a problem in formal charge, and that's going to make this not a very likely structure to exist, but that's in the next lesson, so I don't want to defer to that now. But what I will say is this, is we've got atoms in this structure that are not making their typical number of bonds. We'll find out in the next lesson that that usually means they're going to have a formal charge, which usually leads to greater instability. In this case, so the carbon here has 1, 2, 3 bonds. We learned that carbon having 4 valence electrons, which is 4 short of a filled octet, usually means carbon's going to make 4 bonds like this one is. So that's not the normal number of bonds. And then oxygen, having 6 valence electrons, typically makes 2 bonds to get a filled octet, but this oxygen's making 3. And so we've got 2 atoms bonded to each other, both of which are not making their typical number of bonds. So, and this is probably not going to be the best structure we could come up with for this molecule. So if we start this over again, so what we'll end up doing is having the carbon bonded to both oxygens, so this carbon is now a central atom to both of these, and that one of those oxygens is then bonded to a hydrogen. Now if we'll do the same thing here, and once again we've used 2, 4, 6, 8, 10, 12, 14 electrons, we've got 10 left, and we'll fill up those outer atoms, and now we've used all 24. And again, the only atom not happy is our central atom here, this carbon, so who's only got 6 electrons around him, so somebody next to him needs to share. Well, we've got 2 options for this case. Both of these oxygens have a pair they could share. However, it turns out one's going to be better, and we usually look at it again, one being better than the other from a standpoint of formal charge, but again, that's in the next lesson, so I'm not going to allude to that just yet. But we can talk about making the normal or typical number of bonds. Oxygen usually likes to make 2. Well, this oxygen right here is already making 2, but this one here is only making 1. So we're going to have him be the one that shares. We'll erase a pair, put a double bond, and now all of a sudden every atom in this structure is making the typical number of bonds. This carbon's now making 4, this oxygen's making 2, this oxygen's making 2, and this carbon's making 4. Life is good. And this is the proper Lewis structure for acetic acid. Now, I'm not saying that it's impossible for an atom to make anything other than its typical number of bonds. It is possible. So, however, if you can make a structure where every atom's got a typical number of bonds and another structure where it doesn't, the one where every atom is making its typical number of bonds is better. And when you see this COOH by the end of chapter 2, you're going to have to get good at recognizing that, oh, that means this kind of Lewis structure right here. But cool, this is your typical lesson on Lewis structures, so hopefully this is mostly a review from Gen Chem. But if you're looking for some more practice, and if you want the study guides that go with this lesson, by all means, check out my premium course on chadsprep.com. And if you've benefited from this, give me a like, give me a share, and put a big smile on your face. Happy studying.